All right, so let's talk about the derivative. So you've probably heard of this notion. This is sort of basic to calculus. We want to talk about the derivative. You may be vaguely aware of what it is, but nonetheless, let's just draw out some pictures, let's talk about how it works, and let's take it from there. So what's the derivative? Well, first of all, let's draw out a function. Let's say that this is x and y, and we just have, as usual, y is equal to f at x, and let's say the curve looks something like this. All right, so let's talk about what the derivative of this guy means. Well, I just wrote y is equal to f at x, but sometimes if you want to talk about the derivative, it sometimes makes a little bit of sense to use a physical metaphor. So maybe instead of x, we want to think about things in t, time. So we can sort of think about x, our variable as x, or our variable as t. And sometimes, instead of f at x, we'd want to think of our function as p of t, position. So if this were a function that represented the position of something in space, well, let's talk about the following. Suppose we have some point A, and let's say we have some point a little further down the line. Let's call it A plus h. So just a point h later in time. So if we drew this little line segment on this graph here, we could compute the slope of this line segment just via the rise over run formula. So what would that be? So the slope is of course equal to the rise over run, f at a plus h minus f at a, all over a plus h minus a, which we could rewrite, of course, as f at a plus h minus f at a all over h. Okay, but if this is something we can always just do, and sometimes in a calculus class you'll just be doing this to functions, but back to our physical metaphor, if we imagine this is a position function, and we take this, well, what's happening? This is the change in position over the change in time. So in the physical metaphor, so this physically is an average speed. Maybe we should say average velocity because it's signed. Average velocity. Okay? So basically, what this little secant line is, in this picture you may or may not have seen before, is if we draw sort of a little line segment like this, what this is capturing is it's capturing the average velocity of this function. But of course, and where this is going, you might not want the average velocity. You might want the so-called instantaneous velocity. For example, if you're in a car, the idea that, like the speedometer, what it's spitting out is how fast you're actually going. Not an average, but your true speed. So how do we approximate this? Well, first of all, we can approximate it by taking more points closer and closer to A. So if we took a point here, we could take this secant line here, and we see that its slope is sort of a little closer to actually what we want. We could take closer and closer and closer approximations, but I said closer to what we want. What do we want? Well, I'd argue that probably what we want is sort of this line right here that precisely captures sort of the shape of the graph. I think it could be argued just from the picture that the slope of this line here that touches this graph just gingerly just at this one point is going to be the slope we want to capture an idea of what we'd want to call instantaneous velocity here at this point. But how do we actually compute that? Because we have a problem here. This is no longer a secant line, because instead of taking A and a different point, I've taken sort of just touching the graph right at A. There's no second point, so I can't define this quantity here. There'd be no h. In this case, we'd have that h is equal to 0. And that doesn't make sense immediately, but we can make sense of it. Because how can we think about this? We can think of this sort of instantaneous slope as, well, if you take points closer and closer and closer, the slope gets closer and closer to this desired slope here. So what are we going to do? We're going to take a limit. And if you take a limit of these slopes of secant lines, you're going to get the slope of this so-called tangent line. So how do you do that? What we're going to do is at this point A, we're going to define the slope of the tangent line. We're going to denote it by f prime of A, and we're going to let this be the limit as h goes to 0 of this quantity here. Of course, assuming this limit exists. All right, so this is the idea of the derivative, and this is of course why we have to talk about limits before we talk about derivatives. But in summary, if we want to calculate the instantaneous velocity at a point on a graph, what we have to do is we have to take a limit of these secant lines to limit to this tangent line in order to find its slope. And how to compute that is via this limit here. All right, so let's just do a quick example. So if we sort of draw out a very familiar graph, let's say y is equal to x squared, well, that graph, it's a parabola. It looks like this. So we can sort of eyeball things pretty nicely. We see that near 0, it definitely looks like the tangent line is going to be flat like this, so that we have 0 derivative at x is equal to 0. But then if we take points here, we can see we get a positive slope, and if we go further up the curve, the slope will get bigger and bigger. Similarly, if we go to the left of 0, we get negative slopes, and those negative slopes will get bigger and bigger as we continue on. So that's sort of the rough idea. So we know that if you take the derivative of this function y is equal to f at x, if you plug in this point and find the derivative there, you're going to get 0. You're going to get bigger and bigger positive numbers as you go this way, and bigger negative numbers as you go this way. So how can we do this? So this, even though I've only drawn 5 tangent lines here, let's be honest, this is sort of a messy graph. If we want to think about how the tangent line works, we'd want to do better than having to draw every single little line against every single little graph, because even with only 5 tangent lines drawn, this is a little messy to look at. So let's do a definition. Let's say that we're going to define the derivative function. So let's define f prime of x is going to be, if we just take, so long as it exists, the limit as h goes to 0 of f of x plus h minus f at x all over h. So is this the same definition as I wrote up before? Yes, but we're thinking about it a little differently. We're now thinking of an actual function that if you give me an x, I can tell you at that x what's the slope of the tangent line. So let's actually compute this in an example. And what do I mean by compute this? Well, I literally mean compute this. It's a limit. We know how to do limits. We can do this. So in the case of f at x is equal to x squared, let's compute f prime of x. So this just entails plugging in the definition. So f prime of x, in this case, well, we're going to write equals. We don't know it exists yet, but it is going to, so retroactively will be justified. So we're taking first the definition. Eventually we'll move a little faster, but it's always nice to write the definition down. But what is the definition? Well, f of x is x squared, so this is x plus h squared minus x squared all over h. And of course, this looks a little problematic at first, because if we just plugged h into this, because of the h in the denominator, it looks like things might go wrong, but in fact, let's not worry. Let's take this a further step. We're going to be able to cancel that h out. So if we take the limit as h goes to 0, well, of course, let's FOIL this out. Upstairs, we get x squared plus 2xh plus h squared minus x squared over h. But this turns into, well, the x squared cancels out, so we just get 2xh plus h squared all over h. Then we can factor 1h out, and we get the limit as h goes to 0 of 2x plus h. But now this function is a continuous function in h. We can just plug in h is equal to 0, and we get 2x. And that's our derivative function. And indeed, guess what? 2x is a function that's 0 at 0. It becomes more and more positive as your x gets bigger and greater than 0, and more negative as x gets less than 0. So this sounds about right. We sort of feel justified, intuitively that this is going to work, but I guess it also works because we've just computed it. So that's the derivative of x squared.